Now, to run the analyses that we'll be using in this class, we would normally use SPSS. That's a statistical package that allows you to run a variety of different statistical analyses. And for correlation, what it will provide us is a correlation matrix. So it shows the correlation between the different variables that we want to analyze. So for this particular example, we have four variables, A, B, C, and D. And the correlation matrix is divided in half going diagonally. So those ones represent A correlated with A. So obviously A correlated with A is going to be a positive correlation of 1 because it's the exact same numbers. So either look at the numbers above the diagonal or below the diagonal. So if you want to look at the correlation between A and B, we would go to row A, column B, and that gives us a correlation of negative 0.253. If you wanted to look at A and C, we would go to row A, column C, and that gives us a correlation of 0.210. And then A and D is 0.347. Right? If you want to look at B and C, right, we go to row B, column C. It gives us a correlation of negative 0.017. And then B and D would be negative 0.126. And then if we want to look at C and D, we would go to row C, column D, and that gives us a correlation of correlation of 0.087. Now that you kind of understand the matrix itself, let me tell you what it's providing for us. It's telling us the correlation, right? So the Pearson's correlation is going to be that first value there. So that if we're looking at A and B, it's at negative 0.253. Then it's going to tell us the p-value, right? And they're going to call it sig for significance level, right? So that's that second number here. So this, for A and B, the p-value is 0.009. So that says that the probability of getting a correlation of negative 2.53, which is the correlation between A and B, is 0.009 or 0.09%. So it's very unlikely to get a correlation of negative 0.253 if the null is true. It's only going to happen 0.9% of the time. So therefore, we would reject the null hypothesis and say that we have a statistically significant correlation between A and B. Now the third number that you provided in this correlation matrix is the number of participants, right? So for A and B, we have 106 participants that were included in these analyses. So again, it's the actual correlation itself, the p-value, so the probability of getting that particular correlation, if the null is true, and the number of participants that were in the analysis. Now, to give you a little bit of a kind of a cheat sheet here, the starred values or the little flagged values here will let you know that it is significant. So if you have 1 star, it's significant at a 0.05 level. If you have 2 stars, it's significant at a 0.01 level. 0.01 is basically saying it's in the top 1%, whereas 0.05 says it has to be in the top 5%. And again, we'll talk more about that when we get to significance testing in a couple lectures. So let's test your understanding. So are A and B significantly correlated, right? And we've talked about A and B already. So A and B, the correlation is negative 0.253. The p-value is 0.009. That p-value is less than 0.05. So we would say yes, there is a significant correlation between A and B. All right, so which variable or variables is C significantly correlated with? So you can either go to the row of C or the column of C and just go down. So let's do the column of C. So C is statistically significantly correlated with A, right? Because again, our p-value of 0.03 is less than 0.05. So that means that this correlation of 0.210 is statistically significant. If we go to C and B, the p-value now is 0.866. So that's nowhere near 0.05. So therefore, that correlation is not going to be statistically significant. And then if we jump down to C and D, we have a p-value of 0.376. Again, that's nowhere near 0.05. So therefore, C and D is not significant. Only C and A are statistically significant. All right, so which variables have the strongest correlation? All right, so again, all you need to do is look at the actual Pearson's correlations. So A and B is negative 2.53, A and C is 0.210, A and D is 0.347. Let's see, just skip around a little bit. It looks like it's A and D, 0.347. And the second strongest looks like that would be B and C at negative 0.253. All right, so now try some more examples. Is there a significant correlation between A and B? Again, you're going to look at the p-value here. Now this p-value is 0.000, so it's so small that you run out of spaces to include any values after that third zero. So it's much smaller than 0.05, and therefore you can conclude that it is statistically significant. And it is a positive correlation. So the question is, what is R? R is your correlation, so 0.423 is your correlation. We're going to round that to 0.42. Our degrees of freedom, remember degrees of freedom is number of participants minus 2. We have 106 participants, so that gives us degrees of freedom of 104. And then our p-value is 0.000, so we round that to 0.001. And we say p is less than 0.001 because it's actually smaller than that value. All right, so if we're writing up the results section, okay, we'd say there was, so first of all, is there a significant correlation? And there is. So we say there was a significant positive correlation between A and B. Our degrees of freedom now is going to be, again, 106 minus 2, so 104. Our actual correlation itself, our R is going to be 0.42, and then the P is equal to, or you say P is less than 0.001. Okay, so here's written out again. There's a significant positive correlation between A and B. R, degrees of freedom 104 equals 0.42. P is less than 0.001. Let's try another one. Is there a significant correlation between C and D? Right, so again, you're looking at your p-value. Again, the p-value is less than 0.05. It's 0.005. So that means we have a significant correlation, right? And it's a negative sign, so we know it's a negative correlation. What is R? R, again, is an actual correlation itself. So it's negative 0.270, and you run that to negative 0.27. Our degrees of freedom are going to be the number of participants, which is 68 minus 2. So we have 66. And then our p-value is going to be 0.005. Now, if we were to write this up, again, we know that there's a significant correlation between these two variables. So we would say there was a significant negative correlation between C and D. R, and then the degrees of freedom would be 66 equals negative 0.27. P is equal to 0.005. Okay. Is there a significant correlation between E and F? So now our p-value is greater than 0.05. This is 0.166. So this is 16%, or basically almost 17%. So we would not have a significant correlation between E and F. It is not relevant because it's not a significant correlation. We don't have to worry about the sign. R is going to be rounded up to 0.14. We're going to take that 6 and round it up, so 0.14. Our degrees of freedom is 36, which is our number of participants, minus 2, so 34. And then our p-value, if we're going to round it, is 0.17. So if we were to write these results in the results section, we would say that there was not a significant correlation between E and F. R, degrees of freedom of 34, equals 0.14, because we're rounding here. P is equal to 0.17. We're rounding here again. So definitely get used to looking at a correlation matrix and being able to understand the results and write the results in APA format. So we all have heard the idea that correlation does not equal causation, right? So to kind of give you an example of why correlation doesn't equal causation, I'm going to talk about this positive correlation between ice cream sold, the amount of ice cream sold, and murder rates in the U.S. So there is a significant positive correlation between the amount of ice cream sold and murder rates, right? And if you're not careful, you could try to conclude that, murderers like eating ice cream, or eating ice cream causes people to commit murder. Now, it sounds pretty ridiculous, um, but there are other examples that are less ridiculous where people try to make causal claims simply based upon correlational data, right? So this is just simply a correlation, um, but we should not conclude that ice cream causes murder or that murder causes people to want to eat ice cream. So we talked about before the three requirements for making a causal claim, right? So temporal precedence, again, the idea that the causal variable must come before the effect variable, right? So if we're arguing that eating ice cream causes people to commit murder, then people would have to eat ice cream before they committed the murder, right? It couldn't be they committed the murder and then ate ice cream. Then that wouldn't make sense. So the cause has to occur before the effect. There has to be a relationship between the two variables, right? And the correlation tells us that there's a relationship between the variables. So we know that ice cream and murder rates are correlated. So we meet that criteria. But then we also have to eliminate plausible alternative explanations, right? So there could be some explanation that could account for this relationship. So a correlation accounts for this second criteria for making a causal claim, but it doesn't account for the first or the third. So, temporal precedence is a problem because we can't, based upon correlational data, we can't conclude that ice cream happened first and then they committed murder, or if murder happened first and then they ate ice cream. So we can't fully address that with correlational data. It does address the fact that the two variables have to be correlated, but it also does not address the issue of the third variable problem. So, in terms of temporal precedence, again, the idea is we can't determine simply based on correlational data which one came first. So we don't know if ice cream causes people to commit murder, or murder caused people to eat ice cream, or there's some kind of cyclical relationship where you eat ice cream, then you commit murder, which makes you want to eat more ice cream, which makes you to commit more murder, right? Again, this is a ridiculous example, but there are contexts in which people can make these kind of arguments. So it's important that you understand why a correlation does not automatically lead to causal claims, causal relationships. For the third variable problem, what if you could think of a third variable that could explain why the relationship between ice cream and murder exists? So if you think about, if you include temperature as a variable, right, that could account for this relationship. So when it's warm outside, people eat more ice cream. When it's also warm outside, people tend to be outside more. They get more easily agitated, and that will lead to higher rates of crime and violence and murder. So once you factor in temperature, the relationship between ice cream consumption and murder rates is now no longer significant. So once you, what a correlation cannot do is account for this third variable problem, because correlations only factor in two variables. So again, this is one of the reasons why correlation does not equal causation. So if you want to find out more information about correlations, here are some useful links. Definitely review these links if you want to learn more information about different components of correlations.